charge per mole of electrons. And so like N, I think N really just stands for number. So it's like in an amount, it's like a count of things. So in all of these equations where we're using like Faraday's constant and charge, N represents the moles of electrons, not the moles of atoms or molecules in the reaction. So why do we need Q? Because we need Q here to define it in other terms. So we can define Q as the number of moles of electrons times Faraday's constant, which would give me just coulombs, unit of charge. So you can take this equation from earlier where we have negative Q times the cell potential. We can swap out Q for the number of moles of electrons. This is moles of electrons times Faraday's constant times the cell potential. And that tells us the maximum amount of work that can be done by a reaction. And as I was just saying, Gibbs free energy is also a measure of the maximum amount of work. Maybe not a measure, but a calculation. Yeah.
It's just electrons transfer or all?
Yeah, well, what do you mean all of the electrons? It's in, it's,
6 moles of zinc. You have to calculate the electron for 6 moles of zinc? Or is it just the moles of electrons that are?
it's just the ones that are moving. Yeah, it's just the moles of electrons that are moving. Yeah, we'll do an example and I'll show you that. Yeah, that would be a lot to calculate. Total number of electrons. We just want to know the ones that are moving because it's the electrons that are moving that are doing the work. Yeah. So because this is the W max is also delta G, we say the delta G, standard Gibbs free energy, is equal to the number of moles of electrons times Faraday's constant times the cell potential. And this unlocks a lot of places where we can substitute in cell potential for Gibbs free energy and rewrite a bunch of equations. So essentially, this is the key to relating cell potential and Gibbs free energy. Anywhere that Gibbs free energy exists in an equation, I can plug in negative NFE E cell and sort of rederive that equation now in terms of cell potential instead of Gibbs free energy. And I'll give you things like Faraday's constant. It's not on the next slide, it's this side. So calculate Gibbs free energy for this reaction, and we've got cell potentials. So we're gonna use cell potentials. So again, this is delta G equals negative N, and I'm gonna write this as N with a little subscript E minus, right? So it's the number of electrons times Faraday's constant times the E cell at standard conditions. So we've got to calculate the E cell for standard conditions here. So my reaction, well, I guess this is the part that you guys should know. So how do I calculate the cell potential for this reaction? Yeah. Cell the cathode minus cell the anode. Right, cathode and anode. So it's a redox reaction, right? Exchanging electrons. So there's essentially two half reactions. Something's being oxidized, something's being reduced. What's being oxidized? Yeah. Sodium's being oxidized because here 0, here plus. So that's my oxidation, which makes that the anode. It starts at the anode, electrons are lost there. What is the reduction half reaction? Or what's being reduced? Hydrogen. Because hydrogen here is plus, but here it's 0. So hydrogen is being reduced. What's the cell potential for hydrogen? 0. It's always 0. So my E cell is going to be hydrogen, which is 0, minus whatever my anode is, which is sodium. There we go. I'm blind. Negative 2.71. So the negative is in the E cell calculations, cathode minus anode, because we need to flip the sign of one of them. And the negative in the equation flips the sign for us. So E cell is 2.71 volts. So then over here, delta G is equal to negative number of electrons. And this is number of electrons being transferred. Because in theory, we've got like a beaker and another beaker, and there's a salt bridge, but then there's also the wire. And it's the electrons that are traveling through the wire that are giving me this voltage that are doing or would do the work if you connect it to some load. How many electrons are being transferred? How many moles of electrons are being transferred in this reaction? Two. So if we're looking at the reaction, if I look at the, right, I have two sodiums with 0 charge to 2 sodiums with a positive charge. So that means each of those loses 1 electron, so that's 2 electrons transferred. And assuming that it's balanced, that means that the hydrogens are gaining 2 electrons. So this is 2 times Faraday's constant, which is 96,485. Times E cell, which is 2.71. 2 times 96,485 times 2.71 is a negative 522,948 joules. Yes. So Faraday's constant is coulombs per moles of electrons. E cell is in volts, which is joules per coulomb. And then times, this was just moles of electrons. So a lot of units flying around. That's good timing because I was just about to explain that. Yeah, so When you do this, it comes out in terms of joules, so you might need to convert it into kilojoules. All right, so this slide was for a different question, but so like a previous reaction was spontaneous, and actually, just to point out the fact that, oh yeah, because we had a positive cell, E cell, and then a positive or a negative Gibbs free energy. So cell potential positive, Gibbs free energy negative, both are telling me it's spontaneous. That would be one way to check. Like if you calculate both, those should agree on whether it's spontaneous or not. If those don't agree, then you probably missed a negative. This is really kind of an aside. So the reaction here that I just scribbled it in there at the top is for iodine reacting with bromine. If you calculate what the E cell is for that, it's negative. So the negative voltage, which means it's non-spontaneous. And so in trying to tie this back into what we know about the periodic table in general, why does it make sense that iodine would not take electrons from bromine? Mhm. Bromine's more electronegative. So bromine's going to hold on to those electrons better. So it's not going to give any up to the iodine, which is the same reason that if you saw like sodium stealing electrons from fluorine, that doesn't make sense because sodium very not electronegative. You could even say electropositive, and then fluorine's very electronegative. So that reaction is never going to happen in that direction spontaneously. So yeah, be A. All right, so like I said, because we can now plug in negative NFE for delta G, that means that we can take delta G equals negative RT ln K. We can plug in that negative NFE and then do some rearranging. And this is really where the units get a little bit crazy. So because we got negatives on both sides, we ended up with RT over NF and then the natural log of K. And this is still moles of electrons. And what this means is if we're using R as 8.314, the thermodynamic R, which is joules per mole Kelvin, and that's times temperature, because these are standard conditions, it's 25 C or 298.15 Kelvin divided by moles of electrons times Faraday, which is coulombs per moles of electrons. Then moles of electrons cancels. Oh, right, we're going to end up with volts. Yeah. K, oops, not cancels out that whole thing, just the K, right? Um, Wait, did I cancel out one of these? Is the wrong one? Honestly, so much easier to do this without all of the joules per mole over coulomb. I'm ending up with an extra moles. Write this as joules per coulomb, because joules per coulomb is volts. And then we can even pull out the natural log and make it regular log. Ultimately, we end up with this. That E cell is 0.0592 volts divided by N, which is still moles of electrons. So I think that the moles in here becomes moles of electrons, times the log of K, which is the equilibrium constant. And this number, 0.0592, that's 8.314, which is R, times 298.15 divided by Faraday's constant, which is 96,485. Oh, and times 2.303. So that whole mess is the 0.0592 ends up being volts. Because units. So it's really taking all of these things that are constants, especially at standard conditions, taking all these things that are constants and then just condensing them down into a single number.
Why did we switch to log base 10 at the end? Why could we do that at 25?
So it's not that we just like can do that at 25. That's what this over here on the right, the natural log of K is equal to 2.303. Like this is a conversion from log base 10 to natural base to like switch between the two. So then the 2.303 up here is from that. Now, why do we do that? I think just because our equilibrium expressions, the law of mass action, is expressed in or defined as the log base 10 of concentrations of the products raised to their exponent or raised to their coefficients divided by. So I think it's just to make it line up with that. Otherwise, we'd have to be doing some kind of translation.
Makes it neater with what we already have.
Yeah. Makes it line up more with what we already have. So is it entirely necessary? I don't think so. Because we are just kind of converting it. Yeah. You don't need to be able to repeat that derivation. All right, so this means that now if we have a standard electrode potential, or if we have a cell potential, we can calculate the equilibrium constant. Because again, so 0 is that negative? No, it's positive. 0.0592 moles of electrons, and now log of K. So again, how do we find cell potential? I would say whenever you're trying to find cell potential, figure out what's being oxidized and what's being reduced first. So what's being oxidized? Iron. All right, so iron's being oxidized. What's being reduced? Hydrogen. And hydrogen's nice because hydrogen cell potential is 0. And so if we want to calculate E cell, again, that's cathode minus anode. And then my cathode, whatever's being reduced is the cathode. That's hydrogen, so that's 0. But we need the cell potential for iron. Iron is, was this 3 plus or 2 plus? 3 plus, thank you. Negative 0.036. So this is positive 0.036 volts. And now when I plug this in, The only thing that I'm still missing is number of electrons. Or not really number, it's moles. How many moles of electrons are transferred in this reaction? As long as it's balanced, you really only need to look at like what's being oxidized, how many electrons did it lose? Or what's being reduced, how many electrons did it gain? Six. And again, like we could look at the iron, like I think iron's the easiest because it starts at 0 and it goes to +3 oxidation state. So each iron loses 3 times 2 is 6. .036 times 6. That was not times, that was minus. And that was plus. What am I? Divided by 0.0592. 3.6486 equals log of k. So 10 raised to the negative, not 10 raised to the negative, wow. Thinking pHs, just 10 to the positive 3.6486. So this is 4.452 or equals k. I guess we only have 2 sig figs. So 4.5 times 10 to the 3 equals k. Oh, is this reaction spontaneous?
Yes.
2 ways that we know that. Or at least that is going to favor products, right? Because our K is positive, or K is greater than 1, which means it's going to favor the products. And our voltage is positive. All right, so now we can go all the way around the triangle. In my opinion, especially because it's the way we derived everything, this equation is sort of the key to getting the other ones. I will sometime this week give you a sheet of all the equations and things that I'll give you for the final. I'm not going to, it'll just be like a bunch of equations. So you need to know what they are, you need to know how to use them and when to use them, but I will give you a lot because it's a lot to remember over the whole semester. I think all 3 of these are on there. And just anytime that the cell potential is involved, this N is for electrons and not for number of moles of anything else. It's moles of electrons being transferred. So maybe we could bring some of this together. So like if I know that the equilibrium constant is 1.2 times 10 to the 3, what's true about Gibbs free energy and cell potential?
E cell is positive, delta G is negative.
Yep. E cell is positive, delta G is negative. Because the equilibrium favors the products. And because for all of these, we're talking about standard conditions. Standard conditions means that the concentration is what for things in solution? Standard conditions, the concentration is. A little bit of a throwback. Yeah, 1 molar. And for gases, 1 atmosphere. Yep. So if you think about like, when we're talking about these and we've got this little 0, the O, degree, whatever you want to think of it as, right? That's telling me that this is at standard conditions. So if it's standard conditions, everything is 1 molar, that means that Q is going to be 1. Because any concentrations that I have in the products or reactants will be 1 raised to whatever it is times 1. So it'll always reduce back down to 1. So if my K is supposed to be 1.2 times 10 to the 3, then 1 at standard conditions is not 1.2 times 10 to the 3. That reaction moves forward to go towards that 1.2 times 10 to the 3. So from the standard condition, it'll go forward. Now, if K is 1, then at standard conditions, you're at equilibrium. So it would be 0, and it wouldn't go forward or backwards. All right, so we talked about Gibbs free energy. We had, again, standard conditions, but what about non-standard conditions? As soon as we start to change concentrations, we get away from those standard conditions. So here we're given information about standard conditions. So E cell is 1.1 volts. So is that spontaneous or non-spontaneous? Spontaneous. Voice of the people. Right, so it's spontaneous. And that is, again, with everything being 1 molar. Now, what if I change those concentrations? So if chromium or copper, sorry, not chromium, copper goes up to 2 molar, and then zinc goes down to 0.01 molar. Is that going to make this reaction more or less spontaneous? If this goes now 2 molar and this is 0.01, think Le Chatelier's principle. Did I increase the concentration of my reactants? Yeah. So because I'm increasing the concentration of the reactants, decreasing the concentration of the products, doing both at the same time, right? This is going to make this a more spontaneous reaction according to Le Chatelier's principle. So really, Le Chatelier's principle was just giving us like a rule of thumb for, I guess, what we could do now quantitatively. Yeah. So this would make this more spontaneous. It's going to increase the voltage that I get actually as well. And not by a ton, but we get now instead of 1.1 volts, we get 1.17 volts. So that actually means we can also get a little bit more work out of this reaction because we have more reactants than products. And we can take this, oh, and I'm not going to go through this whole thing, but again, like we can start plugging in this key, and I could say also, if delta G at standard conditions, delta G at non-standard conditions is equal to NFE, the cell potential at non-standard conditions. So this negative NFE and then negative NFE, but standard plus RTLN Q, and then we divide everything by negative NF. And I get E cell is equal to E cell standard minus RT over NF natural log of Q. And this is that same thing, we gave the whole like condensing of all of this, condensing all the constants down. And so that also is going to give me then E cell equals E cell standard minus 0.0592 over number of electrons log of Q. So for this previous reaction then, I made my products made my products 0.01, and then my reactants were 2 molar. So this becomes the log of, that's Q, so 0.005. Which is negative 2.301. And that would be multiplied by 0.0592 over what would be 2 electrons transferred. And so we'd end up adding something to my standard voltage. Honestly, in looking over all of this, I was thinking it'd be a lot cleaner if instead of positive voltage being spontaneous, we had defined it as negative volts being spontaneous. Like that was kind of just a choice. And then all of these negatives wouldn't be flipping signs. Actually, it wouldn't be. Anyways. Big aside there. So that gives us the Nernst equation. So essentially, it mirrors, right? Like this is a mirrored version to Gibbs free energy at non-standard conditions. Yeah, RT ln K. Yeah, or RT ln Q. Right, it's the same form. It's slightly different because we're doing things in terms of really number of moles of electrons being transferred. But it's got the same feel to it. And also the fact that we got some signs flipped. So for a reaction under non-standard conditions, and this is really the nicer way to see these reactions, is in terms of the half cells. Especially when they're labeled, right? I've got the oxidation of nickel and I've got the reduction of vanadium something, vanadate, but it's positive. So that's my reduction. I've got my oxidation. We don't really need to combine these two together, but we can use this to go and find nickel. So nickel is here. That's negative 0.23. And for the vanadium, that's over here. So that's 1.00. So we want to find the cell potential of this electrical chemical cell. These are E cell at standard, E cell standard. Are these reactions at standard conditions though? No. So concentrations are given there after the states. So the, like this is 2 molar, 0.01. That one's 1 molar, but 2 molar over here. So these are not standard conditions. So we do need to calculate what it is at standard conditions. And we could do that from the table. And it's going to be cathode minus anode. So 1.00 volts minus negative 0.23 to give me 1.23. Because we're going to plug that into E cell at non-standard. Make that volts. Minus 0.0592 over how many electrons transferred? Yeah, and actually these, because we're just given the half reactions, this is like the step before you combine them because the electrons aren't balanced between the two. My oxidation reaction says I'm going to lose 2 electrons, but my reduction reaction is only giving up, or is only gaining 1. So this whole reaction actually needs to be multiplied by 2. Which is important for 2 reasons, because this is going to be 2 electrons, but then the log of Q, don't know what that was, right? This is products over reactants raised to the power of their coefficient. So this needs to be concentration of nickel 2 plus times the concentration of that vanadium, but squared because I got to multiply the whole thing by 2, divided by the concentration of VO2 plus squared times the concentration of hydrogen, sorry, not squared, but to the 4th. So we get 2.0 times 2.0 squared over 0.01 squared times 1.0 to the 4th. So Q is 80,000. So I can plug in Q. Um, right, okay. To .08 volts. So now I think the tricky question here to ask is, what does that tell us about K? could calculate K. Because I have E cell standard conditions, we could do the no, it's just log K. So we calculate it. Now I gotta check. I'm forgetting a negative. I'm forgetting a negative. Nope, I was not forgetting a negative. So we can calculate K. Did this, I guess, okay, so the way to think about this is what I'm trying to ask is K larger or smaller than Q? Why do you say smaller? So K at equilibrium, not necessarily 1. Yeah, K can be anything, actually. It's usually not 1. That one question that was on the test, that was a weird one. I just picked one because it made the problem work. But for this, I guess, so E cell we calculated was 1.23 volts. At my current conditions, where Q is 80,000, did the reaction get more or less spontaneous?
Less spontaneous.
Got less spontaneous. So is Q bigger or smaller than K? I want to say it's smaller. But if we go up, then it'll make that 0. Now I gotta calculate K. Yeah. Wait. Yeah.
One, it's spontaneous, and the larger K is, the more spontaneous it is.
Yeah.
So if it got less spontaneous, Q has to be less than K. But
Yeah.
still bigger.
Right. And it's a lot less. It's a lot less than K. K is 3.58 times 10 to the 41. Because if I'm at equilibrium, if this was at equilibrium, then E cell at non-standard conditions would be 0. If you're at equilibrium, then it's not going to go anywhere. So it would be 0. Yeah. But it's more than at standard conditions, which would be everything at 1. All right. It's 11:03. Oh, I said a few more things. I got office hours like all day. That's